It's code time. It's time to write code. Let's see how we can implement the k-nearest neighbors algorithm in Python inside of a Jupyter notebook. And this is where the code lives. And this video is all about giving you a high-level overview of what the code does. There are 8 different sections to this code, and we go all the way from reading the data in, pre-processing the data, making a model, fine-tuning the hyperparameters, visualizing the performance of this model on the validation set. Oh, I forgot, we also split the data into train, validation, and test sets. And finally, we save the model to disk. In a separate notebook that lives here, we are actually going to use the saved model and then apply that on the test dataset, which the model hasn't seen, to actually see how good the performance is. So this code actually contains all the essential components of a complete data science pipeline. It's not exactly a pipeline in software terms, but you get the idea. So let's go ahead and take a closer look at the code. Oh, and for this example, we are going to use the Titanic dataset. The Titanic dataset is freely available at this website, Kaggle, as you can see. And this dataset has been used and reused many times in many courses as kind of the hello world of the machine learning world, okay? So what does this data tell us? Well, I'm not going to talk to you about the Titanic disaster and what happened to the ill-fated Titanic on its maiden voyage when it hit an iceberg and sank. You can go watch the movie. There's the Titanic movie starring Leonardo DiCaprio and Kate Winslet. Or if you want to stick more closely to the facts, go ahead and check out the Kaggle website that has a lot of details about the data and where it comes from. So in a nutshell, the data is about, I think, 1,300 rows or something, which means it has data about 1,300 passengers who traveled on board that ship. More than 2,000 passengers actually did travel on board that Titanic. However, we don't have data for all the passengers. Now, some of those passengers did not survive, and some of those passengers did survive the sinking because there were these lifeboats that could actually carry the passengers to safety, but there weren't enough lifeboats. Okay. So the goal of this challenge, as you can see, is to predict who survived the sinking and who did not survive the sinking. And we are actually going to use our first machine learning algorithm that we learned, which is k-nearest neighbors, to see if we can build a decent classifier. And we are going to focus on how accurate we are going to get. We are aiming to get maximum accuracy score out of this modeling. So we are going to get started with our code notebook, and as we just discussed, we are only going to get a very high-level overview of what are all the different components of this notebook. So all the Python code lives inside a Jupyter notebook, and this is how the Jupyter notebook looks like. There are 8 different parts to this notebook. First, we understand the problem, and then we import all the modules. Importing modules simply means that you are importing code that someone else has already written and put that inside of a package. And then we are going to read the data into this notebook. And then we are going to split the data into training, validation, and test. Why? Well, you have to build your machine learning model with some data. And if you actually evaluate how good or bad your machine learning model is on that same data set that's no good, right, is going to give you a good result because you are actually training and evaluating on the same data set. So the training data set actually lets you learn the parameters of the model. The valid dataset, or the validation dataset as it's sometimes called, lets you learn the hyperparameters of the model. In this case, in the KNN case, we are learning the value of K, and that is usually done manually. And then you also have the test dataset. Once you are done refining your model, you're completely satisfied with your model, you're actually going to test the final performance of your model on the test set. And then we will do data pre-processing, super important step. Okay, we are going to do 6 steps here actually inside of this data pre-processing. And then we build our first model, and we see that the first model is not so much good. It's not good because we are actually using default values for the hyperparameters, and that turns out not to be the best for our data set. And then we are going to do some hyperparameter tuning using the validation set and the training set. And then we finally, when we are done picking the right hyperparameters, the right value of K in this case, we are going to combine the validation set and the training set and make a combined train and validation set. And we are going to retrain our model with that data and then finally evaluate the performance of that model on the test set. Now, in this notebook, we are not going to actually evaluate the performance of the model on the test set. Instead, what we are going to do is we are going to save that model to disk in a very special format. In the next code video, what we will do is we will open up a separate notebook and read that model and then evaluate the performance of that model on the test data set. Okay, so off we go. So this is the first block of code, and essentially we are doing two things here. We are requesting you to go to this Kaggle web page that contains the Titanic dataset that we talked about and understand what the problem is all about, right? I mean, unless you have a very good idea of what you are going to do, there's no point in trying to read the data in and then doing all the data science stuff, right? So that's what we do first, and then we import all the code from different packages, and some description is actually given here. And then I'm going to go and hit run. It's taking some little bit of time, and now it is run. Okay, it did throw out some warnings, but I'm not too worried about those warnings because we are good to go. And then the next step is about reading the data into the notebook. And the Titanic dataset exists as a comma-separated value file, which means that it exists as rows and columns, and it can also be opened inside of an Excel worksheet. So I am going to hit run here, and when I hit run there, I'm actually taking a sneak peek at what the data actually contains. This is super important. One of the very first really key steps in data science is actually to take a look at the data and see what's in there. So here you can see there are at least two different kinds of things in there, right? So one are things like, name column, which is like, strings, as we call them in computer science. And there are also these numbers. And again, within those numbers, you can actually see, if you look carefully, there are at least two kinds of numbers. So one is numbers like this in the age column, 28, 38, 26, and numbers like this in the fair column, 7.250, 71.28, etc., etc. So those numbers are continuous variables, right? They can go all the way, like, 7.2000000. So those are the continuous variable columns, age and fair. And then there are columns like survived and passenger class or P class, where you have numbers like 3, 1, and for the sex column, you have male, female, right? So those are more like categorical columns where we can either have 1 or 2 or 3. The passenger either traveled first class or second class or third class. Those numbers 1, 2, and 3 have a very different meaning than saying that this passenger has an age 1 or he paid $2, right? They are very different meanings, those numbers. So those are there are different kinds of numbers and they need to be treated differently. And you can also see that there are about 1,300 rows and 12 columns, which is super important, which also shows that this is not this giant data set. Okay, this is pretty small data set. It's easy for a beginning data scientist to actually learn most of the algorithms on this data set. And we'll actually see that some of these columns can actually be further divided, or you can extract more information from some of these columns. Okay, it's a process called feature engineering. For example, in those days, names had a very special significance on whether you will actually survive or not. Why? That might be very funny, right? I mean, if you have a certain name and you have a much higher likelihood of surviving, well, it's all because of this. In those days when the Titanic was actually sailing, the long names meant that that person was a very special person. So people who belong to royalty or who belong to the upper strata of the society had much longer names than the common man who had much smaller names. That can sometimes throw people off because some people tend to drop this column completely. and think that, hey, I mean, what does the name has to do with whether a person will survive a thinking or not? Turns out in those days, it did make a big difference. So let's print out a list of the column names. You don't have to actually do this. We go to the really important step. This is good machine learning practice. You need to split your data into at least 3 sets, okay? 3 non-overlapping sets. The training set, a lot of the data goes into the training set. And this data is going to be used to build the model. And then you have the validation set or the valid set. It's sometimes also called as the holdout set or the first holdout set, okay? As I just termed. And then some of the data actually goes into the validation set and some of the data goes into the test set. Now the test set data is data that you pretend you don't have right now. It's only going to come in tomorrow, because once you make your model ideally should be useful for something that is going to happen in the future, right? Or things that it hasn't even seen. That is what machine learning is all about. Trying to predict how the stock is going to perform tomorrow. Trying to predict if your housing price is going to go up or down tomorrow. Trying to predict what is going to happen to this patient in the next 6 months or after 1 year. So most of data science, not all, is all about predicting what is going to happen next. So there is a brief description on why we actually do that and how we define the functions. I'm going to click run, and then we are going to put away 30% of this data set for both validation and testing. So I'm going to click run, and I'm going to click run here. And the goal is that we have the bulk of the data, about 917 out of 1,309 rows. This data will go into as a training set, and the half of the remaining data set will go into the validation set and half into the test set. So you don't have to pay a lot of attention right here, because if you are really interested in going line by line, as I said, we will have a separate video for that. And so make sure that you actually print out the head of the data and the shape of the data at every single step, because sometimes you will find that you are not getting what you expect to get. So once you do something to the data, it's always a good practice to actually check what the data looks like just now, either by taking a few of the first rows, or more appropriately, take some random rows, a bunch of random rows from the dataset, and take a look at it and see if the data is actually looking as how you would expect it to look after what you last did to it. And then, as I said, the test data is data that we are not going to be seeing until our model is complete, until we have done hyperparameter tuning, model selection, and all that stuff. So we are going to write that data out now, okay, into this Titanic_test.csv. And once we are done with that, we now move on. Now, pre-processing is a big deal, because this can kind of make or break. And this basically arises because of a couple of reasons. One reason is that all machine learning algorithms can only chew numbers, okay? You simply cannot put in strings and all the other things that go with them into a machine learning algorithm. It simply wouldn't understand. It's going to throw out an error saying that, hey, I don't even understand what you are trying to do with me. So make sure that all the data that you have been converted to numbers. So that is one. And two, the data has to be in a certain form. We'll actually see what that means. So before that, there is one major problem that needs to be addressed before we can go any further. And this has got to do with missing values in your data set. They are sometimes called null values. Sometimes fashionably, they are abbreviated as NA values or NANs sometimes, okay? So we need to deal with them. The first thing is to check what proportion of your columns have null values. So I'm going to hit run, and you can see this beautiful plot. It's made with Seaborn, which is my favorite Python data visualization library. So it looks like one column, the cabin column, has got about 80% missing values. Ooh, those are a lot of holes, okay? And we have to find a way to deal with those holes before we can actually run a machine learning algorithm on this data set. And the age column has got some missing values or holes, about 20%. And if you look very carefully, strain your eyes, look cross-eyed, the embarked column has got a tiny bit of missing values too. So what can we do about it? Well, if a column contains 80 or 90% of missing values or holes, there is simply no way to do anything with that. So one really good decision is to just drop that column, okay? So the cabin column will be dropped. We are not going to use the little bit of data from the cabin column. What about the age column and the embarked column? Well, there's a way to fill up the holes or fill up the missing values. It's called imputation. I think I had that term. It's a very complex sounding term, but it simply means that you are filling up the missing values. So impute is the term that we use. It's a nerdy term, right? Oh, we are imputing the null values of a data frame. So the age column has about 20% missing values. We are going to impute that. The embarked column have some missing values too. We are going to impute those values too. Now, that immediately raises the question, how can we impute the values? So there are different ways to impute, and we are actually going to have a separate video that talks about what are the different ways of imputing values, or what are the different ways that you can fill up missing values. One way for continuous variable columns like fair or age. One simple way to do this is just to take the average of those values, of the remaining values, and use that average value to just, plug in the holes or, close those holes. Or you can take the median value. Very rarely is the mode used. There are more complex ways of actually doing this, and there are packages like Fancy Impute that lets you experiment with different ways of filling up these missing values. As I said, we will have a separate video that talks about this real world data challenge, okay? So please stay tuned for that video. And this tells you some of the other pre-processing steps. And so I'm going to hit run here. We are just dropping the cabin column. Just make sure that you have 11 columns remaining. And we are going to see what are the data types for each column. So if you see a data type like object, not good, we have to convert that into a more usable data type. When I say usable for machine learning. So a lot of these cells actually contain descriptions of what is actually going on. So please read them. And we are going to define some functions for pre-processing, and we are going to apply those functions. This is typically how it's done. Okay, I'm going to keep hitting run, and you can see that all the object data types have actually vanished. So which is good news. And then we want to make sure that the categorical mappings are right. So what do I mean by categorical mappings? Well, if you have different categories like, female, male, and even say null values, we actually first have to map them to numbers, okay? What do I mean by that? Well, which means that null values are going to get converted to 0 when you decide to convert them, and females are going to get mapped as 1, and males are going to get mapped as 2. And in the next step, we are going to take this mapping and then apply that mapping on the data set to actually change the values. So instead of seeing females and males, you're actually going to see 0s and 1s, okay? So that's how we convert strings into numbers. And these are some impute functions. And as I said, the goal of this specific video is not to describe them in great detail. So I'm just going to hit run. And then I am going to apply the pre-processing function. And then I am going to take a look at what are the values that we use for imputation. So in the training set, at least, there was just one column, continuous variable column, age, which had missing values. So we calculated the median value for age, and we are storing that in this dictionary. Why? Why are we bothering to store it? Well, because all the things, all the pre-processing steps that you did to the training dataset have to be replicated in exactly the same way on the validation and the test set. Okay, this is good data science practice. And we have to use the median value of age from the training set if we are to impute or fill up missing values for age in the validation and test sets. Okay, do not calculate the median value of the age column in the validation set to fill up missing values in that set. Okay, because the age column median value of 28 should have the same meaning for the model across all the different data sets. Okay, this is something that you should remember. And then we are going to split the data into X and Y. I'm doing it very explicitly here. You don't have to do that. So the column that we are trying to predict is the survived column, and that becomes the Y for the training set. Okay, it's sometimes called as the target variable or the dependent variable, and all the other variables are bunched together into the X. So these are called independent variables, the X columns, and we are going to use the independent variables, put them inside the machine learning model to predict the dependent variable. Okay, we are going to print out the shapes. Yes, looks good. Now we do something called standardization. Standardization is nothing but making sure that the numbers in different continuous variable columns are in the same range. For example, age can go from 1 to say 90, whereas the fare paid by passengers might only go from 10 to say 30. Okay, so these are numbers in two different ranges, right? So one goes from 10 to 30 and the other one goes from 5 to 100 or maybe 5 to 120 or something. So some machine learning algorithms, especially the k nearest neighbors algorithm, actually works well only if you have the continuous variable columns in the same ranges. Otherwise, it's going to give extra weightage to the column that contains bigger numbers. Okay, but some other algorithms like random forests do not have this limitation, so it's okay if you do not put this step in. Okay, so we are going to do that, and then this is one way of doing it, and we are going to store the details of how we exactly did the standardization into a variable, because we are going to save that to disk, because we are going to later reuse the same scalar or the scaling statistics, which essentially means that we are doing taking the mean and the standard deviation. We are going to store that away separately because we are planning to reuse that for the validation and the test sets. So then we are going to pre-process the validation set in exactly the same way we pre-process the training set. So step number 1, we start off by dropping the cabin column, and then just checking to see if we actually drop the cabin column. Looks like yes, there's no cabin column here. And then we are going to check for null values. That is step number 2. Yes. So it looks like the age column has null values. There is no cabin column. But now we have a new problem, right? So the fare column, which did not have any holes in the training data set, now has a little bit of missing values here. Okay, I'm just going to scroll up just to show you the comparison. See, the fare column for the training set has no null values, whereas the fare column for the validation set does have null values. So how are we going to deal with this? Because we only know of a way to deal with missing values in the age column, right? And we also know what to do when you have missing values in the embarked column, but we have no idea how to deal with missing values or holes in the fare column. So there are two different ways to proceed here. One is to go back, because fare happens to be a continuous variable column. We can actually go back to the training set, calculate the median value of fare, and then use the median value to fill up all the holes in the fare column of the validation set. Okay, but we are going to take an easy way out here. We are simply going to drop that row that contains the missing value in the fare column. So I'm going to hit run, And now you see that we have lost one row of data. Instead of 196, we only have 195 rows of data, okay? And then we go down and go into the next step, which is we are going to make the mapping. That is step or stage number 3 of pre-processing. And we are just going to make sure that the mapping is consistent across the validation set and the training set, right? Because if you actually put females as 1s and males as 0s in the training set, and you put females as 0s and males as 1 in the validation set, things will really go wrong because the model does not understand this, right? And then we make sure that after making sure that the categorical mappings are consistent, we are going to proceed with the imputation. Okay. Now, there is one thing that I want to explain here in both the training set and the validation set, and it's going to happen in the test set as well. There is a new column we have added, age_NA. This tells you the status of whether these values were imputed or whether these values actually came from the original data. So this value 22.0 it says false, which means that this 22 came from the original data set. So if you scroll down, you can actually see that in places where we use the median value from the training set for filling up the holes, you will actually see that age_NA reads as true, okay? So that kind of captures the uncertainty in this imputation, right? I mean, if you use the median or the mean to impute, there's no way to claim that that is the best way to fill up the holes in that column, right? There might be so many other ways to fill up those holes. So this column actually captures some of that uncertainty, okay? Which means that we don't know whether that's the right way to impute or not. And we are going to separate out the X and Y very explicitly. You don't have to do that. More experienced programmers can simply select those columns and use them when you are running the machine learning model. Okay, so I'm just going to hit run. And finally, we are going to standardize, and we are going to use the same scalar, the same mean and standard deviation of those columns. But one thing I want to point out here is that we are going to standardize only the continuous variable columns, okay? Please do not scale or standardize the categorical variable columns. Okay? There is males and females and null values 0, 1, and 2. Please do not standardize them, okay? Because they mean something very different. So make sure that you are applying your standardization only for the continuous variable columns like fair and age. Okay, I'm gonna hit run. And I am excited because we are going to build our first model of number of neighbors. This is the value of k we have been talking about. And this is another hyperparameter. There are at least 3 or 4 more hyperparameters, but we are only going to try to tune just one of these hyperparameters in this video, okay? And this is how it's done. I'm gonna hit run, and then I am going to see the performance of this model on the validation set. Okay, this is very, very important. We make the KNN model using the X train and the Y train, but we are going to see how well the model is going to perform on data that it hasn't seen yet. And one data set that we have that this model hasn't seen yet is the validation data set, or X-valid, okay? So we are predicting on the validation data set. Okay. Now, because we know what the Y values of the validation data sets are as Y-valid, we have the predicted values and the Y-valid value, the actual validation Y values. We can easily use those two sets of values to see how good our model is performing. So I'm going to hit this, and you can see a confusion matrix. So confusion matrix is actually one way to evaluate how good your model is doing and exactly where your model is going wrong. So we'll have a separate video, a very detailed video on the different ways to evaluate your model, and we will be explaining the confusion matrix. It essentially tells you how confused the model is, okay? So that video, feel free to please make sure that you check out that video. That's going to be uploaded much later. That tells you how to read this confusion matrix. But for now, let's just move on and calculate a bunch of single measures that tell you how good or bad your model is. So we are going to look at the accuracy score, the Matthews correlation coefficient or MCC, and also the F1 score. Now, the accuracy score is for a data set that is perfectly balanced, okay, which means you have equal number of people who survived and equal number of people who did not survive in the same data set. Now, for data sets that are imbalanced, where you have more of one and less of the other, these other scores like MCC or the Matthews correlation coefficient and the F1 score are much more meaningful, okay? We are going to get everything printed out here anyway by clicking run, and we see that our accuracy score is terrible, right? 0.3435. Accuracy scores go from 0 to 1. If you are making random predictions, say based on a coin toss for every row of data of the validation set, if you say that I'm going to toss a coin, and if it lands heads, then it survived. And the next row, you do the same thing, and if it lands heads, it survived, and if it lands tails, it is not survived, okay? So if you do that, you will get an accuracy of around 0.5, okay? Now, the more the accuracy, the better, okay? If you get an accuracy of 1, your model is perfect. If your accuracy score is 0, you're getting every single thing wrong. And 0.34 means that you are actually better off tossing a coin, and you don't have to take the trouble of making all this machine learning models, right? So that is clearly not good, because machine learning is supposed to do better than a random coin toss, right? So what do we do? There are different ways of making your model better. And one way of doing this is by hyperparameter tuning, which means, hey, we used the value of k equal to 5, which means for calculating whether this unknown point was actually survived or not survived, we looked at 5 neighbors nearest to it, 5 nearest neighbors. But who said 5 is the right value? Okay. Because k can have values from, say, 1 all the way to 100, 200, how many you want, okay? But very large values of k have very little meaning. But here we are actually going to try a bunch of different values of k using the for loop here. And the goal is actually to pick the best value of k on the validation set. Okay, so you can easily see these are the different values of k that were tested out. Every time you make a model with a different value of k, test the performance or measure the accuracy score on the validation set, and then just put them in a table. And you can see that at k equal to, and you can see that at k equal to 2, you have the best accuracy score of 0.512, which is slightly better than average. Okay, so you are going to pick this value of k for your final model that you are going to use on your test set that comes up in the next video, okay, in the next code video. And I love making plots, so whenever you are given a choice of showing data inside of a table and data as a plot, please always show the plot. Okay, people love looking at plot than at data. So you can see the same thing, k equals 2, it has maximum accuracy. And then before we do anything else, we are going to combine the training and the validation set. Why? Well, the validation set has served its purpose, right? So when something has served its purpose, what do? You either throw it out or you make it useful again. So we are going to combine it in this way. We're combining the x's and the y's. And finally, we are going to build the model with both the training and the validation set data. But please let me point out here that we are now using this tuned hyperparameter, number of neighbors equal to 2. We are not using a value of 5, which is the default, okay? And we fit that, and then we are also going to make a different folder for this model. We are using joblib to save this model in a very different format to make sure that the model, all the model's parameters, internally learned parameters, are also saved. Okay. And if you reach this point, great news, congratulations, you have gone all the way from reading data in, pre-processing the data, building a model, fine-tuning the hyperparameters, and finally saving the model to disk. In the next code video for KNN, we will actually read this model, the saved model, and we are going to apply that on the test set and see how well our model does. And from there, we'll actually see what are the different ways that you can improve your model. Okay, this is one way to improve the model, is to tune the hyperparameters. The other way to improve the model is actually to do a lot of feature engineering. So if you go to Kaggle kernels, people have done so much of feature engineering, essentially adding more and more columns and maybe deleting some columns. And feel free to explore those. So that is it for this short code video. As I said, this only gives you a high-level overview. There will be a later video that gives you a line-by-line description of what we did. And there will also be another video where we actually look at the next code notebook, where we are actually going to take this model, the saved model, and we are going to apply that on the test set. For those of you who are really keen to actually go to the next half of this code, the code actually lives here. Okay, so in case you're interested, please check this out. That is the second part of this 2 notebook series, and that notebook actually contains code where you read this, the saved model back in, and then you apply that on the test set. Okay, that's it. Thank you. Hope you enjoyed this little video.